Hello, my name is Haoran Li. Today, I'll be presenting on the topics about transport layer protocols other than TCP and UDP.
Before I begin, I want to ask you a question. Other than UDP and TCP, what other transport layer protocols do you know? A few seconds to think about it. Some people miss it quick, which we heard quite often in the class. The fact is that there are so many transport layer protocols, but developers are still complaining that there are too few choices to choose from. Given the fact that there are tons of transport layer protocols, only UDP and TCP succeeded. Before I took this course, I had no idea what Quick is, which I'm sure still a lot of us haven't learned it yet till tomorrow. Another question? Since we are talking about Quick fairly often, which is a new protocol, but how new is this new? Anyone knows in which year it was designed and in which year it was standardized? I will briefly introduce these transport layer protocols in later of the presentation. There are a lot of transport layer protocols in history. Some are made natively, and some evolved from TCP or UDP. TCP, UDP-based protocols are taking quite a big percentage out of all the transport layer protocols, since people may want to either extend its features or improve its drawbacks. UDP Lite. UDP Lite stands for Lightweight User Datagram Protocol. It was designed to serve applications in error-prone network environments that prefer to have partially damaged payloads delivered rather than discarded. If this feature is not enabled, then UDP Lite is semantically identical to UDP. It's initially designed for multimedia such as VoIP, Voice over IP. Since sometimes users may want to receive a partially corrupted packet rather than no packet, while UDP and TCP will discard such a packet. The overhead of UDP Lite is 8 bytes, which is the same as UDP, but the difference between UDP and UDP Lite is from its header. The UDP header with 8 bytes is source port, destination port, length, and checksum respectively, and each of the part taking 2 bytes. While the parts in UDP Lite's header are source port, destination port, checksum coverage, and checksum. If the checksum coverage is set to the packet length, then it is the same as original UDP. However, the minimum checksum coverage length is 8 bytes, except the special case is that the entire packet is covered when the checksum coverage is set to 0. For example, if a user wants to receive any packet, regardless if there's an error in its payload data, the user may want to set the checksum coverage length to 8, and in such case, UDP Lite will always send the packet unless there's an error in its header. However, the modern link layer will perform CRC, or the cyclic redundancy check, and discard the frames with error. But it is still possible to use UDP Lite with some extra configurations. To use UDP Lite protocol, some extra drivers need to be installed to make the link layer aware of not to discard these packets. Furthermore, people recently found out that IoT may potentially benefit from UDP Lite. UDP Lite was standardized in July 2004 in RFC 3828. UDP Lite is implemented in FreeBSD and Linux, and can be accessed from Windows through third-party library. MicroTP. MicroTP, or Micro Transport Protocol, is a new protocol developed by BitTorrent Inc., which is mainly used by its product BitTorrent client MicroTorrent. It is an open UDP-based P2P file sharing protocol and was developed when BitTorrent had trouble with TCP. Some future implementations has made to provide reliable in-order packet delivery, and an upgrade congestion control algorithm which is called Low Actual Delay Background Transport, or LADBAT, to measure the traffic between peers. The purpose of MicroTP is to reduce the latency and provide better congestion control P2P connections. The LADBAT algorithm is documented in RFC 6817, It is based on monitoring the difference of timestamp between receiving a packet and sending a packet and determine the traffic condition. For example, if the sender sends 5 packets at 10, 20, 30, 40, 50 milliseconds, the receiver receives at 100, 150, 130, 150, and 180 milliseconds, resulting in a difference of 90, 95, 100, 110, and 130 milliseconds respectively, which is increasing. Thus, the algorithm will infer from this positive increase and adjust its transfer rate. However, LEDBET is only a congestion control algorithm. In the above example, the receiver may not only receive packets from the particular sender, but other senders as well. Since MicroTP is a commercialized protocol and is only used by BitTorrent, it is not proposed to be standardized. However, it is an open source protocol where the source code can be found on GitHub, and it is licensed under MIT license. If anyone is interested in the source code, you can go to the link below. MPTCP. MPTCP stands for Multipass TCP, and it is an ongoing protocol which is backward compatible to TCP, and it is being developed by IETF Multipass TCP Working Group and still in its experimental stage. It is an extension on current TCP protocol with the feature added on, the multipass. The goal of MPTCP is not to simplify TCP, instead, it is adding more functionalities to TCP. The regular TCP can only support one channel in link layer to communicate, while MPTCP can increase the throughput by summing up all available link layer channels, which is where the multipass in its name comes from. Right now, our imagination is kind of limited to an extent, and I'll show you how and why. The multipass here trying to address the issue. If my desktop has a few interfaces to grab the resources, why can't it grab all the resources at the same time? Assume Alice's desktop has a wireless interface and an Ethernet interface. As we learned from the class, each of the interface has a different MAC address. Our TCP connection is to use either Ethernet or the Wi-Fi, leaving the other available resource idle, which we now think it is normal because no current protocols can utilize both. However, MPTCP is here for that. With MPTCP enabled, it can use both resources. Let's use a famous example from the course. Now, Alice is watching MI15. Maybe through the Ethernet, it can grab her the first half of the movie, and the Wi-Fi can grab her the second half of the movie. Let's try to extend this a little bit. But this is what I'm thinking maybe we can do in the future. The normal situation is that we might have a few available Wi-Fi nearby and we're only able to join one of them. But what if we can grab all the available Wi-Fi and distributedly download stuff? And how fast would that be? We never know. Again, this currently might not be viable either due to the limitation of the wireless interfaces or the Wi-Fi technology or the protocols. But it is a direction that we may work on, a distributed connection. Back to MPTCP. This is a currently being developed technology, and since it hasn't been fully deployed yet, we never know how far it will go. This is a huge topic, as huge as quick, so I'm not going too much details on it, but a brief introduction. MPTCP is especially useful in wireless networking environment, including both Wi-Fi network and cellular network. Their companies and developers are exploring the usage of MPTCP in the upcoming 5G cellular network. Furthermore, there is potentially performance enhancement in a data center environment where MPTCP can use multiple passes across multiple interfaces to reach a higher throughput than a regular TCP connection. One of MPTCP features is its redundant overhead, which is 50 bytes plus 40 bytes option, with a comparison to TCP, whose overhead is 20 bytes plus 40 bytes option. The MPTCP defines a 4-bit field called subtype, which includes the few subtypes of MPTCP, and each of the subtypes has its own header fields and header sets. These subtypes currently are MP capable, MP join, DSS, add address, remove address, MP prior, MP fill, and MP fast close, taking the value from 0x0 to 0x7, with 0xf reserved for private use, leaving 0x8 to 0xz unassigned. Here are some examples of MP-TCP subtypes fields. It can be seen from these pictures. They have different header sets as well, which is not normal in other protocols. There are a few RFC documents discussing the features and usage of MP-TCP, which can be found on IETF websites. The version 0, which is the experimental version of MP-TCP, was standardized in January 2013 in ISC 6824, where all the images from the previous slides come from. There is a newer version being proposed in June 2019, which has not been approved yet. MP-TCP is a relatively new technology and has not been fully deployed yet, so its popularity in its community remains unknown. However, almost all modern OS have MP-TCP implemented, including Linux, macOS, and Windows. Quick! I'm sure our classmate will cover this topic more than I do. Now, I will only briefly introduce this protocol. QUIC stands for Quick UDP Internet Connection, which is developed by Google. QUIC is very similar to TCP plus TLS, which stands for Transport Layer Security, plus HTTP2. It is still an internet draft, and the reports are being worked on. There are a few key features of QUIC. As described in Chromium website, QUIC can dramatically reduce the connection establish time, improve congestion control, multiplex without header LAN blocking, and migrate connection. As known, a TCP connection is using three-way handshakes. However, with TLS and HTTP, it can be much more complicated than that. Before actually receiving the data, it might take 2 or 3 round trips to communicate to establish the connections only. However, using QUIC, it can immediately talk to a server which it has connected before. To answer the question from the very beginning, it was originally deployed in 2012, and the experimental version is publicly announced in 2013. An internet draft was submitted to IETF in 2015, and until now, for about 8 years, it hasn't been standardized yet. Though it is not officially standardized, some web browsers already implement and support QUIC, which includes Chrome, Microsoft Edge, and Firefox, taking up more than 80% of the web browser market. Some people may argue that it is not a transport layer protocol, instead, it is an application layer protocol. There's a reason for that. Though not announced publicly, people are recognizing HTTP over QUIC as HTTP 3. But again, this is only an IETF draft. Furthermore, a transport layer protocol should not be limited by what application the top level is using, but it seems QUIC is only applicable if the upper layer, the application layer, is using HTTP. There are also a few protocols that have completely different implementations than TCP or UDP. ATCP, or the Apple Down Control Protocol, is developed by Apple Inc. and was designed specifically for Macintosh OS. It was originally released in 1985 and was mainly used by Apple devices in late 1980s and early 1990s. The maturity of TCP IP suite in 1990s quickly drove ATCP out of the marketplace, and the failure of ATCP was officially announced by Apple Inc. in 2009. By then, the Mac OS X, which is Apple's core product, does not even support ATCP any longer. Most of ATCP features are designed to be self-configured, and most of the development efforts were put into LAN environment, given that the internet was invented in 1983. Some of the ATCP self-configuration features were later migrated to other Apple products such as Bonjour. ATCP was standardized in IETF in 1991 in RFC 1378. FCP is also known as Fiber Channel Protocol. It was originally designed to carry SCSI small computer system interface data over optic fiber channel. It is a common high-speed data transmission protocol, and the speed can go up to 16 gigabytes per second. FCP is extensively used by SAN, the Storage Area Network, through a switched fabric. By using FCP, it ensures a high throughput than a LAN backup. Other than SAN network, FCP is also used to connect supercomputers, storage devices, and workstations, where they have a special need for data transfer rate. Also, to deploy the FCP in such environment, the connection should be using either optic fiber or the copper media. By using FC, it brings benefits on both performance and scalabilities. It was standardized in RFC 4172. Fiber channel have a few different generations, and each generation has a different transfer rate, and the naming convention is labeled roughly the same as their transfer speed. Furthermore, each generation should be at least backward compatible to two earlier generations. SCTP, the Stream Control Transmission Protocol, aims to provide reliable data transfer like TCP and message-oriented like UDP. The features that differ SCP from TCP and UDP are multi-homing and redundant passes. Multi-homing is the same idea as multipass as discussed in IMP-TCP. SCTP transmits signaling message from and to SS7, which is the signaling system 7 for cellular network. It can optimize by avoiding multi-threading problems when the traffic volume is high. It uses a 4-way handshake instead of 3-way handshake, which is used in TCP. It was standardized by IETF in 2007 in RFC 4960. Even though it has been 13 years, some developers are still considering it in its infancy stage. Why SCTP is now popular? SCTP cannot cross the net, which is extensively used in reality, and the community seems to still remain immature, lacking enough library support and development. Furthermore, the multi-homing feature increased the complexity for developers to implement the stack, and also MPTCP is addressing the multi-homing needs, which is competing SCTP. Due to the above reasons, SCTP is being used by a few companies but not many. Many modern OS have implemented SCTP, including Linux and Windows, and Macs have access to SCTP by installing the third-party driver. Other than the above 7 protocols, there are still a lot of other protocols which are not introduced, such as RDP, RUDP, CUDP, DCCP, etc. However, none of the existing protocols made greater success than TCP and UDP. Though many developers may complain that in the modern world there are too few transport layer protocols to choose from, the reality is that there are quite a few. However, these protocols are either designed for special usage or having some fatal drawbacks, or still developing. Furthermore, the cycle of developing and standardizing a protocol is too long to comparing to the fast-growing needs in the internet world. Also, when protocol needs to be standardized, it has to remain open-sourced so that other OS producers and applications developers can implement that, which sounds unprofitable to the companies. Though Apple has made its own effort, the ATCP, it was before the TCP has dominated the internet world. However, if delve deeper into MPTCP, it seems people from the Apple are still contributing to the transport layer protocols. Given the fact that TCP and UDP are the two most popular and dominant protocols, network engineers still have a long way to go to find and develop sufficient substitutes to accommodate for the variety of needs.
That's all about my presentation. If you have any questions, please feel free to reach out to me via email. Thank you so much for listening.